Hello, my name is Gordon Sharp, and we're going to talk about diversity in this video and basically how it can be used with the Lab ROI tool by Aircuity to determine peak capacity requirements for laboratory facilities. So basically, the ROI tool has many different uses. It can be used to evaluate energy savings, but it can also be used to determine system diversity or effectively peak capacity requirements. And that takes into account many different functions and requirements. We look at both the fume hood requirements, the thermal load requirements, and also the air change or ventilation requirements. So the Lab ROI tool looks at each of these individually and assesses which is the maximum requirement. And sort of like it does for saving energy and looking at energy use, it also looks at the capacity requirements. So we'll look at all these issues when we get into the model itself, but let's first talk a little bit more about the air change and ventilation requirements, because with respect to the demand-based control, which is what we'll be talking about in its application here, one of the key things to keep in mind is that, again, typically the lab air requirements, in terms of the amount of time that we need to purge the lab, it's typically is about 98 to more likely 99% of the time. So about 1% of the time, we find that labs will need to purge or go to a high flow to basically clear the lab. So we can use that fact to basically predict and determine the amount of time and the amount of capacity we need to fulfill that requirement. So the way we do that is by looking at something known as the Hunter's curve or the binomial theorem. Again, this is not a new concept. It's been used for many, many years and for plumbing calculations in terms of determining pipe sizes. The good way to think about this is it relates to, if you have a building and you have, numbers of faucets and toilets, the question is, well, how do I design for capacity? Do I assume all the toilets are flushed at the same time and people are running the faucets all at the same time? And the answer is no. I mean, that would be yield a much higher capacity than is required. So instead, you look at the question of, well, how often are those toilets going to be flushed? How often are the faucets used and other plumbing fixtures? And then you can calculate the amount of capacity based on a certain level of certainty or really a certain amount of time that you can expect that that you're going to exceed that capacity and obviously minimize that. So again, this is done by in plumbing all the time, and we can apply those same principles to the use of ventilation requirements in terms of this purging requirement. So the key thing here then is, again, as I said, this function is known as the binomial distribution. It's available in Excel. It's a very common mathematical function, and it basically can be used to assess then the capacity. So again, this is not, you might think is a risky thing, but it's really not risky at all. And in fact, it relates to how we design any building in terms of its climate, in terms of the capacity requirements. In other words, typically we look at a thermal requirement in terms of climate that would say, all right, we're going to not design for the worst case day of the century. We're going to design for conditions that typically represent 99%. So typically you have a design criteria that represents 99 or maybe 99.5%, which means that if we had it for 99%, that means that out of the 8,760 hours in a year, we're designing the building so that out of 87 of those hours, we're not going to meet the thermal requirements, and that just makes good logical sense. Hopefully, it shouldn't exceed the conditions that often or that by that much, and that's just the way we normally design buildings. So we can do the same thing when we're designing labs, only here we're applying it not to a thermal condition, we're applying it to a ventilation requirement. So in this case, you can see that what I've done is I've taken the 1% condition, that is a typical situation we see in laboratories for purging, and said, well, how many labs would I expect to purge at the same time? And basically, what I'm showing here is that if we had, let's say, 25 labs, the question then becomes, well, how many labs could be purging at the same time? Well, obviously, you expect any number of labs could, but again, to expect that many of those labs would be purging at the same time would be extremely rare. And that's, again, where the binomial distribution comes in to calculate that and give us some percentages to design, just like we would for climate design. So as an example here, if we wanted to have the lab meet the design conditions 99.9%, which is a very high level of certainty and high level of confidence and high level of design compliance, we can see that for that condition, we would, using a 1% design condition, which is what we typically have for lab purging, you see that out of the 25 labs, only 3 labs would we expect to be purging at the same time. And that would happen 99.9% of the time. So only 0.1% of the time would we expect that the lab would not meet that would have maybe 4 labs running at the same time. Now, if we want to go to even greater certainty and have even less amount of time that happens, we can see that if we go to 99.99%, so that only 0.01% of the time would we have more than the design condition, you see that design condition would relate to about 5 labs. So only 5 out of the 25 labs would ever be purging at the same time. That condition would occur only 0.01% of the time. Now, obviously, as we increase the number of labs, we get more averaging, and that has a big impact on, again, reducing this number. So you see that in the highlighted case here, that for the 99.9% condition, that doubling the number of labs, you might think would make that number go from 3 to 6, but actually only goes up to 4 because, again, of that averaging effect. So we're saying that if I have 50 labs, only 4 of those labs would be purging at the same time, and that would only occur 0.1% of the time. So again, so either 4 or more would only occur 0.1% of the time. Going to even 100 labs, again, only 5 of those would be purging at the same time. Again, 5 or more. So again, you can see that it doesn't take much to get high levels of certainty, to have the amount of time that you're going to exceed these requirements, again, becomes very small, and you can do that without many labs. So let's now take this information and use this in the lab ROI tool and show how we can use this to determine capacity. So now let's look at the ROI tool itself. So we've opened it up and we're here on the Assumptions tab. And as I said before, we have looking at both fume hood, cooling, and then of course the ventilation requirements, and the capacity is based on the worst or the highest of those 3. Over here on the left, we have factors that affect that fume hood diversity number, or the fume hood capacity number. We have the number of fume hoods, we have the maximum CFM for a particular hood, and we also have this average day sash opening. So basically that's the average. A default value we have set in the model is that the peak is going to be 25% higher than that, or in this case it'd be 75%. You can obviously change that number. That number is set over on the Advanced Assumptions tab. So if we were to go over to that on the Advanced Assumptions tab, you can see here this number here, advanced average peak fume hood opening. It's saying 75%, but that's actually relating, you can see, to 25% higher than the fume hood diversity factor. Again, you can just go in and change that number if you want. But the point here is that those we found to work as good numbers. Again, obviously you can change those, but those are built into the model as at least default assumptions. Then we have the cooling, and the cooling is based on, obviously we have different types of zones. We have low load, medium load, and high load zones. And we have percentages of those, and obviously the number for the total project. The key here in terms of capacity is really this average peak. You also have a room peak, but that relates to the equipment, like say the requirements you'd have for your, let's say a chilled beam or a chilled ceiling type system. Those would be used in the room peak requirements, which are obviously going to be higher for a specific room, are going to use to set those. If we look at the air handler requirements, which is really more what we're talking about here, that would then be based on the average across the types of fume hoods, or I'm sorry, across the types of labs in a particular type of load zone, like a low load or medium load. So this is saying that for the 40 zones, the average peak capacity across those zones would be about 4 watts per square foot. So again, this relates back to the air handler. So effectively it's saying what's the air handler requirements, not the room, specific room, but in terms of the average, or with that, so some diversity applied, which is really what relates to that 4 number. So again, obviously you can set the different numbers. We have a higher number here for the medium load, 8, and we have 12 for the high load. So obviously those are going to be the factors that affect the capacity. And then when you take the the weighted average of these, that gives you a number that again is going to give you the cooling load capacity. So we now look at the ventilation requirements, and again, what the factors going to be affecting that in terms of the peak requirements are going to be this obviously this minimum requirement for the occupied period, which is set for 4 air changes in this case, and obviously your purge requirement, which in this case we set to 12. Now the model built into the model is this 1% assumption. It actually can be changed, but that's pretty much set in the model. But if you had an unusual situation, again, you can come back to Aircuity and we can adjust that in the model. But typically we find this 1% based on the millions, even billions now of hours of data is a pretty good estimator of the amount of time we see a lab in purge mode. So we feel that's a pretty good number, and so that's what it relates to. If you want to be more conservative, you can always up the percentages a little bit, as we'll get into over here. So this is this design percent. Remember we talked about this. This was the, gets back to the binomial theorem. This gets back into the sort of design basis. So, in a cooling, in terms of the cooling requirements, you might design for a 99% design requirement, saying you're going to meet the requirements 99% of the time. Here, we can typically we'll set this higher for these minimum ventilation, again, just to be more conservative. So here I've set a 99.9. Again, we can even go more certain, like 99.99. Again, whatever you want and feel comfortable with. Again, in this 99.9, that's saying that we're going to meet the requirements all but 0.1% of the time. So that's literally all but 8 hours of the year. So obviously a very small amount of time. But again, you can adjust that if you want to be more certain. Now we get into these other factors here. These green colors here are indicating assumptions we can set that relate to the dollars per CFM. This is really a way to quantify the peak requirements. So you have different, you might want to see, well, I have a certain amount of CFM capacity, but what does that relate to? I want to make some design decisions, and I want to have to know a little bit of what that impact is to be able to do some trade-offs. So this gives you a sort of rough idea. We've set some defaults here, and you can obviously change those. Those are the ones in green. You see these are white. That's because they're based on a formula, and those relate back to these numbers. So when we set the cooling system capacity, it's function not only of the dollars per ton, but also of the required amount of tons for this system based on the climate. Obviously, some areas will have more requirements in terms of, obviously a greater thermal load than others. So this gets into the dollars per ton because of the amount of requirements for the different zones, climate zones. So obviously that's taken into account. It's already calculated for you. All you have to do is put in the dollars per ton, or if it's heating, it's the dollars per MBH. So once you have those in there, that calculates what the amount of dollars per CFM in terms of the cooling, heating, and other types of systems. So those relate to cost factors. The last thing we have on the assumptions tab is the diversity percent. It's sometimes confused, a little confusing to people. What that relates to is it's an ability we've put into this model to allow you to sort of take advantage of different amounts of certainty and concern you have over the different systems. Now, if you think about the cooling system in a lab, it's important, obviously very critical. We want to be comfortable, but it's not a safety issue. So you might be willing to take a little more diversity and a little more capacity reduction on the cooling system than you would maybe on an exhaust fan, as an example. So we've given you the ability to adjust that on a per system basis. So when I say 100%, that means I'm taking the full amount of diversity possible, all 100% of it. So let's say that we have in a system, let's say that the worst case, everything's on full, that would be, let's say, 100 kilowatts. But we can take diversity, and that diversity, the model is saying that we can take diversity and we can bring it down to, let's say, 60 kilowatts. So that's a savings of 40 kilowatts, a reduction of 100 down to 60. Let's say, so for the cooling system, you say, yes, I want to take advantage of that 100%. So that would put me at that 60 kilowatts. But if I only want to take 50% of it, I only want to take half of it, I want to be a little more conservative, then I could put in 50% for this instead of 100%. And that would mean that I would now have a capacity not at 60, but at 80. If I, on the other hand, said I don't want to take any diversity on the cooling system, then I would set that for 0. In that case, then would be at the still 100 kilowatts. So this can be applied to each of the different systems. Where you'd see more of this be applicable is probably on the exhaust or supply fan. where you might want to be a bit more conservative there. Although even there, again, if we're a little off and we miss the capacity slightly, again, it's just going to change the flow slightly. It's probably not going to be a major factor, but again, that's an area where you might want to take a little bit more conservative bend if you're inclined to do so. But again, there's other ways of doing that. One way, again, is just in the design percent. So personally, I think that's a better way of achieving it, is by using the design percent and going to a higher number like 99.99. That means you only have literally less than an hour that you're going to exceed the requirements. Again, very small amount. But again, that's your choice, and you can apply this in different ways. But this is our assumptions, and our defaults are based on these numbers. Okay, let's next go to the diversity overview tab. Now, this allows us to see a little bit of what's happened and gives you a way to see what the diversity impact has been. So on the base design, we're now showing the peak cooling requirements. This is across all the different types of load zones. And you can see that the average across those different zones, the weighted average comes out to about 5.2 watts per square foot, which in this case works out to about 30,000 CFM. In this case, the ventilation requirement, this is without demand-based control, would be at 8 air changes. That's pretty straightforward. And then we also have an unoccupied, which obviously is not going to be a factor for peak capacity. And then lastly, we have the fume hood requirements. So again, as I said before, the fume hood requirements are based on looking at the maximum flow of each hood, adding those up, applying the average diversity factor, which is in this case 60%, and then to get to the peak diversity, I add 25% to that. So that's actually 75%. So that 9600 is used based on the maximum fume hood flows for each hood times 75%. Again, that can be changed as we showed before in the Advanced Assumptions tab, but that's the way it worked out. Now, in the proposed design, we have those same fume hood and cooling numbers, but now we add in the diversity reduction. So we're not dealing with this 8 air changes anymore for a minimum requirement. We're now reducing it down based on the ability of demand-based control to reduce that. And here is where the binomial theorem has come into play, and it's basically now creating this calculation showing that for, in this case, 50 zones at 99.9%, that will mean we'll have 4 or fewer zones at the proposed maximum 12 air changes. And obviously, if we have 4 then are running at 12, then the other 46 are going to be running at the normal 4 air changes, at least at the minimum. So you can see that that's going to give us a 26,000 CFM change. Now, again, as I mentioned before, if you want to be more conservative, we can go back to the Assumptions tab, and I can then change this instead of 99.9, which is already very conservative. I can even go more conservative and make that 99.99. So let's see what that impact is. So if we go back to the Diversity Overview tab, you see that that has only increased it from 4 to 5 zones. So it's made a pretty minor impact on it. So you can see that you can get pretty high levels of certainty and very high levels of design peak requirements in terms of its certainty or in terms of conservatism, that with minor impacts on the design. So we can do that. So let's leave it at 99.99, and you can see that now, again, we've got 26,000 is the number. So if we go down here, we can see that broken down into the different zones, because obviously this calculation of the peak requirements is based on looking at each zone individually, each type of zone, I mean. So we can look at the normal zones, moderate and the high load zones. It's again related to the cooling requirements. And you can see what the different requirements are for both the base and the proposed, and then obviously the savings. Now, one small thing you see here, you see that some of these savings in the moderate and high are actually negative. Why is that? Well, again, the reason for that would be is that when you those proposed zones, the demand-based control, in this case, it's the dominant factor is going to be cooling, but there is a small impact also related to the fact that there are some peak requirements there. Remember, there is some purging happening, so that's going to bump it up a little bit, and that's what you're seeing there. So it's a pretty minor effect, but just to understand where that's coming from. So you can see that we also have, in addition to the 3 thermal zones, we have obviously some other requirements. I don't have any other zones in this model, but if those might be covering some other types of zones, non-lab or maybe other types of constant volume lab zones. Then obviously we have the corridors, which are going to be another obviously amount of airflow into the system. So we add all those up and we get our total requirements. And you can see here that we've got about a 29% peak reduction or in savings, again, which we've calculated out to be about $346,000. So pretty interesting. Now, again, we can, if we want to get more detail on the savings number, we can, and how the capacity has affected that, we can go to the diversity savings tab. So if we go to the top of that, we see now the different types of systems here, and they can see the dollars per CFM that was worked out on the assumptions tab. We have the flows here that we saw from the previous page. Again, the 50,000 for the base design, 35,000 for about there, almost 36,000 for the proposed design. And you can see then that the cost then that relates to, and then obviously the savings. So here's our about $346,000 of savings. Now, again, this is assuming I've taken diversity across everything, but again, on the next one down here, this next table now, because it says partial diversity. So let's go back and put in some partial diversity. Let's say on the exhaust fan, I'm only going to take, instead of 100% diversity, we're going to take almost 100. We're going to take 70% on the supply. I'm going to be a little more conservative. Let's say I take 60%. So we're not going to take the full amount, but let's see what how that impacts the savings. So you can see that now on the savings here in this partial diversity, the system costs have now gone up for the exhaust and supply fan. So exhaust here, we have 241 and 187, which again are greater than these numbers. And that's because we're now not taking that full amount. You can see we're only taking 70% and 60% versus we took 100% over here. So that's why these flows are higher. So instead of the 35,000 or 36,000, we have a higher flow here because we're not taking the full amount of that diversity that we could. So obviously these numbers of savings now 61 and 39 are less than these numbers here. Now we can see that graphically. If we go down here to this graph here, we can sort of see that. So here we have the base design, which is upwards almost 1.2 million. We have now our full diversity. We're taking advantage of that, and we're down to about 800,000. And on my partial diversity, again, we can see that although the heating and cooling system have the same numbers, we have a higher number now for our exhaust, and you can see a higher number for the supply, again, because we haven't taken the full amount of diversity. So that puts us at a little bit higher rate. So again, a little way if you want to be more conservative. Again, I think the using that percent, that 99.99 or 0.9 gives us a good way to achieve that as well. But again, this is just another way to achieve some flexibility and meet your requirements and get your level of comfort. If you're not using the partial diversity, this table over here, this graph, I mean, also gives you a little bit simpler. It doesn't put in that partial diversity. So these can be clipped out and put into reports, or obviously they'll show up in your report as well. So with that, I think that hopefully gives you a better understanding of how diversity can be used in the ROI tool and used to adjust and affect and used for designing peak capacity requirements in labs, where we have taken demand-based control and used its savings both for energy as well as capacity. Hope you appreciated this video and enjoyed it. Thank you very much, and bye-bye now.